Alright, let's take a look at sample problem 6.05 and then we'll look at 6.06. The difference being one is a flat turn. We still have some constant radius of curvature. They give us that as 100 meters. We have a mass of a car going around this corner as 600 kilograms. They give us the coefficient of static friction because at each one of these tires some frictional force is pushing us inward towards the center of the circle. So there's the center of the circle, and it is what is causing our acceleration. We could be holding a constant speed, so the magnitude of our velocity is constant. We could be accelerating also. That would give us a tangential acceleration term, but right now we're just looking at the centripetal acceleration. What they want to know is if it has a spoiler or a wing providing downforce on it, we'll call that downforce the force of lift. If it has that wing and it's going around this corner just about to slide, how much downforce is it actually pushing? And I think when we do the free body diagram, it'll make sense why the downforce actually helps us take a sharper turn or go around the turn in a faster speed. And they want to know this when the speed is 28.6 meters per second. Okay, so if we looked at the vehicle from the rear, or from the rear, let's look at it like that. Let's say here's our tires, here's the back of the car. It's got some spoiler on the back. Your car may have a spoiler. Another example of a spoiler is something like a drag car with a little tiny wheel up front, big tire in the back, huge gigantic engine. But then there's also this big huge spoiler on the back, and as wind goes over it, it acts like a wing and it pushes down. So effectively increasing the normal force. So the normal force of the vehicle, or on the vehicle, is going up. If that goes up, then you get more friction, and then this tire can spin faster and effectively put more of its power to the ground. So we're looking at the vehicle from behind. This is its spoiler right here. Let's go ahead and represent its mass center though. We have frictional forces at the tires. We'll say they're all the same, so we can just sum them all up and call it one frictional force. In other words, let's do this. We have mg acting down. Now they said they told us this, but it's also should become somewhat common knowledge that the force of lift acts down too, so we can say that points downwards. The whole point of the spoiler is to push the car down to the ground so we can take faster turns. There's also a spoiler in the front to keep it from doing wheelies along with the wheelie bar. You want to keep the tires in the front on the ground because they're really tiny and skinny. They're like bicycle tires, and they're just there for steering. They don't put much friction down at all, right? That's the whole point. They're so thin and small that they don't put down much friction. They don't decrease or cause any losses in our system. We want as much power to be delivered and as little to be taken away. Okay, so what other forces do we have on this car? A normal force, right? Going up. Now typically we find out that the normal force is equal to mg on a flat surface. That's not the case, right? Let's figure out what it is equal to. Let's sum the forces in the y direction. It's going to be equal to the mass times the acceleration in the y direction. And we have a normal force going up. We have mg going down and some force of lift going down. That all equals to 0 because there's no acceleration. It does not come off the ground. There's no acceleration in the y direction. We can get an expression for the normal force right away. We're going to need it in a second. as mg plus the lift. So think about that. It's your normal weight. This is your weight right here. But since you have a force from the air pushing down on the vehicle, you also have lift adding to that component in the normal direction. Okay, we'll hold on to this equation right here, and let's sum the forces in the x direction. That equals the mass times the acceleration in the x direction. We only have one. We have the frictional force, and it's pointing to the left or to the center of curvature, so I'm going to call that a minus. That'll equal our mass times acceleration, but for the acceleration, since we're on a curve, let's use v squared over rho, or v squared over radius. Alright, we have the speed, we have the radius, we know the mass. We can calculate the friction right now. So we could calculate the friction as it'll be going to the left, put a vector on it if we want. I'm going to take the vector sign off actually, because we haven't talked about on a curved path something has what's called normal and tangential components. This would be in the tangential direction, this would be in the normal direction or radial direction. So I'm just going to say that we have a magnitude of the frictional force, and that would be equal to mv squared over r. It's going to be acting to the left, so the minus sign does indicate that. But we have a mv squared over r. We have those numbers. We have 600 kilograms. We have a radius of 100 meters, and the speed, or v, is 28.6 meters per second. So we can calculate the magnitude of the frictional force right there. But that's not what it asked for. It asked for what is the force of lift if it has this much friction, basically. So let's put these two equations together. I'm going to go back a step to this one. So get a different color. Oh, that's not a different color. Let's get a different color. Say this is equation number 2, and this is equation number 1 right here. So we can rewrite this equation. I'll go ahead and copy it down. Minus frictional force is equal to mass times v squared over r. Remember, the frictional force is equal to mu times the normal force. In this case, it's static because our vehicle is going around the corner without skidding. It's not breaking free. So in the direction, the radial direction, the one that's holding us in the turn, the one that we are accelerating in this case, it is static friction. There is no sliding. If it told us we were sliding around the corner, it'd be a little bit harder of a problem, but we would use mu k, or the kinetic coefficient. Okay, what do we have? I can say that the mu times the normal force is equal to mv squared over r. And when we look in the y direction, we'll take this equation and say we want to solve these two equations for the force of lift. Scroll a little bit, but still keep it all on there. Doing so, if we solve this for the force of lift, we're going to equal, just rearranging it, the normal force minus mg. And we have an expression for our normal force now. I can take this mu and throw it on the other side, and we get a normal force is equal to m over mu times v squared over r. Substituting that in for the normal force, I get the force of lift is equal to the mass divided by mu times v squared over r minus mg. Now we have a common factor of m, so we can factor it out and say v squared over mu s times the radius minus g. And they plug in some numbers with the speed we're given, with the coefficient, with the radius. We know what g is and we know the mass. Plugging in numbers, we get a downforce. It's often referred to as a downforce, caused by a spoiler, of about 660 newtons. So as this vehicle, real rough drawing here. As this vehicle is traveling around the corner, it's got this thing right here. I don't know what the shape is. It's some sort of airfoil, and it is effectively causing the vehicle to act heavier and heavier. It's pushing it down on the ground. Heavier in the y direction only. It's not affecting, the force is in the y direction, right? This is the force of lift. It's not going to affect any of our x direction motion or horizontal motion. In this case, it is just pushing it down. It'll literally make your car sit lower the faster you go. So these are your fenders in respect to your tire. Your fender's going to just get lower and lower the faster you go. And the problem starts out saying, can we design a car that can go upside down in a tunnel? We have a road, and maybe the tunnel has a perfectly smooth wall to it, so we could drive the car up and maybe put it inverted. So something like that. In this case, the force of lift would be pointing directly down on the vehicle. In this case, our weight is hanging down, but they want to know, what if we were all the way upside down like this? We have mg hanging down. We have a force of lift equal but opposite if this is the case. In order for us to be able to drive on the ceiling, when we sum those forces in the y direction, we'd also have a normal force right here, right? That normal force can equal 0, because that would be the point at which you start not making the curve or start falling off again. So we, as long as it's not negative, right? As long as it's not pushing us down this way, we want the summation of the forces. We have the force of lift minus mg to equal 0. In other words, the lift has to equal the weight. Can we do that? Can we build it? I think so. We got Formula 1 cars that put down incredible amounts of drag. If you watch Formula 1 racing, they can actually go around the corners faster when they themselves are going faster. It's kind of crazy phenomena, and this is because there's spoilers at the front giving us a force of a downforce, and then there's spoilers in the back giving us a downforce. The whole thing's created to be aerodynamic and just stick to the ground. Okay, the next problem I'm going to do has to do with a banked curve. So if we have a vehicle on a banked curve, how fast do we have to go around that curve? And we're going around it like this, into the page. How fast can we go around that curve at some angle theta in order to have no frictional force on the tires? That's the whole point of banking the corner. If we can bank it to a certain angle, you can literally go around that corner and turn the turn without even touching the steering wheel. So that's what we're going to be doing next, and we're going to have to break up the components a little bit different than we're used to.